Okay, maybe let's start. Okay. Hello, good morning and good afternoon and good evening. So this is the recorded presentation. It is a live stream on the YouTube channel and also recorded over there. So today we are very happy to get Professor Uisdean Nicholson from Harvard Water University come here to talk about the Amur River, or the Chinese name Heilongjiang, and talk about the sedimentary erosion and its delta, and also testing the mode of drainage capture and the plate boundary deformation. Before I introduce Uisdean, and I would like to mention the next Wednesday, we have another source to think talk given by John Schwartz and Dave Morin from the Water Institute of Gulf and the University of Texas at Austin. So they will talk about Rio Grande system in Texas. That will be a very interesting river system. And at the same time, next Friday, Christophe from France, he will talk about the routing of organic carbon from the Congo River. And so I get that I'm very interested all the way mega barrel side in the deep sea fan. So Uisdean is he graduated from University of Aberdeen. I guess Peter is your advisor, right? Peter Clifton is well known, and many people know him, and particularly Asia, the Chinese colleague, know him also very well. And so currently, Uisdean is the assistant professor in the Institute of Geoenergy Engineering, Harvard Water University, Edinburgh. And so his research interest is mainly sedimentary and marine sedimentary, particularly understand the relationship between the tectonics and geodynamic climate and paleoceanography and sediment routing and the geohazard. And I want to see he involved in many IODP projects and his current field work and workshops. But also one amazing thing that you can see here, he's did very well for the public relationship that, particularly give many interview to the BBC, talk about the geohazard, like the tsunami, landslide tsunami, and, like Indonesia landslide, and even Antarctic climate change. So I think he's a rising star. So now I think, Uisdean, now I stop sharing. Now you can begin to share and put a presentation mode.
Okay. Thank you, Paul. And thank you for inviting me to give the talk. Can you see my screen clearly, everybody?
Yes.
Or Paul? Yeah, great. Okay, well, thank you for, as I say, for inviting me to give this talk. And so today I'm going to be talking about the Neogene to recent sedimentary evolution of the Amur, which is the Russian name derived from the Mongolian, or the Heilongjiang River, which is the Chinese name, and its delta in the far east of Russia. So the delta, the river system you can see in the background here, I'll show you in a minute. It flows to the east coast of the far east of Russia, and it has for 20 odd million years deposited a delta in the North Sakhalin Basin, which is this area in northern Sakhalin. You can see the island of Sakhalin here north of Japan in the Russian Far East. So this is just an image on the bottom left showing an aerial photograph of the Amur River in its lower reaches. So this nice anastomosing broad river system of about 1 kilometer in this case. And on the bottom right, there is the Heilongjiang, the black dragon after which the river is named, the black dragon of Chinese folklore and legend. The name, of course, refers to the color of the river, at least in the Chinese portion of the river where it sits on the border with Russia, where it's particularly dark in color. Okay, so let me just see if this works. Okay, just a few acknowledgements before I start the presentation proper. So this project was this was done during my PhD. So this finished in 2009. So a few years old now, and it was a NERC scholarship, a case scholarship involving an industrial partner, and that industrial partner was Sakhalin Energy. So I have to acknowledge them particularly for their help in doing a lot of field work in the island of Sakhalin. And the work was done with a whole lot of different colleagues who helped it with different analytical techniques and so on, and access to lab facilities in Aberdeen, where the PhD was carried out, in Sakhalin, in the Russian Far East, and this is the office of Sakhalin Morneftegas in the town of Ocha, and at Moscow State University in Moscow, of course. So first, these acknowledgements, and then just a quick introduction. Paul's already done it, actually, so I don't really need to talk about this in detail. But I'm just from a little island here in the northwest of Scotland, the Isle of Lewis, on the edge of the Atlantic. And I did my PhD, as I say, in Aberdeen, but that was also in collaboration with colleagues at Moscow State University and in Sakhalin. And the PhD was looking at landscape evolution and sediment routing across a strike slip plate boundary. So looking at the delta of the Amur River deposited across an active strike slip plate boundary here in Sakhalin. So what I'm going to talk about today is much more focused on the Amur River itself, rather than all the dynamics of plate boundary deformation. But that was in a wider context of trying to understand the delta and its deformation. Okay, I then spent 7 years working in industry with Shell in the Netherlands and in Malaysia, but a significant amount of that time was spent looking at projects in the Russian Arctic, so including some of the big Russian rivers, the Ob, the Yenisei, the Lena, and so on. So all very important river systems. I should say here, the backdrop to all these images is actually a map of the world's 30 largest river systems. So I'm going to use this a few times in this talk, so that you can see the drainage outlines here of the Mississippi, for example, the Colorado, and so on. And since coming back to academia in 2016, back to Heriot-Watt in Edinburgh, I've been working mainly a little bit further down the sediment routing system than I was previously. So I work a lot at the moment on marine sediments, so looking at turbidites, submarine landslides, and concherites, so sediments transported along the slope by bottom currents. And these just shows you a distribution of the kind of projects I've got active at the moment, but that includes a number of big fluvial systems, or some of the recent publications here on a number of big fluvial systems, including the Tigris, Euphrates, the Mahakam, serendipitously the Yangtze, along with Peter Clift a few years ago. So what I'm going to talk about today, or the way I'm going to structure this today, is I'm going to give you just, first of all, an introduction to the Amur, the river system itself, and then the hypothesis that I'm testing. It should be one hypothesis, actually. I'm really going to focus on drainage capture models for the Neogene that have been proposed, particularly in the Russian literature. And then inextricably linked to that is, or trying to read the depositional record in the North Sakhalin Basin. You really have to understand what's happening in the delta in terms of tectonics. So I will touch on that just to give the context as well. But this is a source to sink project, a classic source to sink project. So we're going to look at the river, we're going to look at the sediment routing system, the Amur River itself, we're going to look at the catchment, and we're going to look at the sink in the North Sakhalin Basin. We're going to do this through two different approaches. One is to look at the sediment composition, so the provenance of sediment, both in the modern day river system, but also in the basin, in the Paleo-Amur deposits in the basin. And then we're going to look at the quantity of sediment being delivered to the basin over time, so a sediment budget for the Neogene. And tied to that is we're going to look at some seismic stratigraphic evidence for sediment routing as we start to see evidence of plate boundary deformation in that area. Okay, and then it's worth pointing out, and I'll kind of come back to this at the end, that this is really quite a high-level preliminary study of the system. There are lots of outstanding questions and lots of, as many or far more questions than there are answers as we go through this presentation. But so this is a very understudied river, and a lot still needs to be done here. Okay, so in its global context, the Amur system, which is here, again, just to point it out, is the 10th largest river system on Earth based on drainage basin area. So it's about 1.8 million square kilometers. And 4,000, so also the 10th longest river system is 4,400 kilometers long. It's also the largest river on Earth to have its delta on a strike or on any kind of active plate boundary. We have some large rivers in Southeast Asia that are very much affected by plate deformation or intraplate deformation. And we have a number of other river systems highlighted here that also are have a delta deposited on an active margin. But obviously these are quite different. Any catchment affected by tectonic forces of whatever magnitude are likely to be less stable than big river systems that develop at passive margins, for example. So that's the kind of null hypothesis, I suppose, that this is likely to be a relatively unstable system. And we'll come to some models of drainage capture shortly. Before we do that, let me just show you what the river system looks like. This is us now zooming into the Amur drainage system in detail. So this is just a map from GeoMap app showing the digital elevation model in the background, the river catchment, the outline of the river catchment in blue, and the drainage system itself in black here. The white lines here show the countries, the country borders. So the river drains the northeast of Mongolia, the Mongolian plateau. It drains the north of China, Heilongjiang province in China, and it drains a number of different provinces or regions of Far East Russia. So a really large area, also quite a complex area in terms of topography. There are lots of different mountain belts that kind of confine the whole drainage system, but that also separate sub-basins within this drainage system. So there are areas of active subsidence, like here in the Mid-Amur Basin. There are areas of former subsidence, like the Zia-Burea Basin and the Songliao Basin in China. And then there are hinterlands with high mountain ranges. So another important note to point out here is that the river actually drains almost the entirety of the Amur plate. So up in the top left-hand corner there is the outline of the Amur microplate, which is sandwiched between the Eurasian plate and the Okhotsk plate in the east. And so the river system drains almost the entirety of that. Of course, the boundaries of that plate, which you can see from active seismicity here around Lake Baikal, are relatively elevated, which forms the drainage divides here. And the river system, so 4,400 kilometers long, starts at its headwaters in the Argun River here, which drains Mongolia and Far East Russia, and then the Shilka River, which drains also the Yablonovoy Mountains here in the west, sorry. And these at the confluence of these two rivers at this point here is where the Amur proper starts, and the elevation here is about 300 meters. The elevation drops to around 100 meters by the time we get here to the Khingan Gorge, near the town of Khabarovsk in Far East Russia. And then there's the confluence with the Sungari River, which drains a significant part of Heilongjiang province. And then the confluence with a number of other river systems, big tributary systems, as it flows down to its river mouth opposite the island of Sakhalin. A couple of other points to note on here. One is just to comment on the suspended sediment load of the river. It's about 52 million tons per year. That figure comes from a paper of Niles Hovius, I think, from about 20 years ago. And the discharge of the river is shown here on the bottom right. So we have very very seasonal discharge, with almost no discharge, very little discharge in the winter, as the river's almost completely frozen over, and a high peak of discharge in the late summer as the as all of the meltwater and more precipitation during the summer results in a really large discharge during those months. A kind of order of magnitude of change in discharge during the year. Another important point to note is that there are no major dams. There are various, or there, at least last time I checked this, there were no major dams. China are looking at a number of projects, a little bit of development around Blagoveshensk on the Chinese side, and China, I think, have dammed some of the tributaries of the Sungari, which are also called the Songhua. But the main tributaries and the Amur trunk stream itself has not been dammed. Okay, so what are we going to test, or what's the angle for today's talk? Well, in the Russian literature in particular, going back 10 or 15 years, there have been a number of different drainage capture models proposed to have occurred in the Amur catchment during the late Miocene or the Pliocene, a bit uncertain on the timing and the evidence for that. But the idea here is, I mean, if you look back at the map here, the Amur flows, as shown on the previous map, across a number of mountain ranges, particularly through this narrow Khingan Gorge, and then along the Sakhalin Mountains here and into the Tatar Strait in this area here. But the drainage model proposed in the literature is that the relatively low elevation range of hills here, the lesser Khingan ridge or range here, separating the Songliao Basin and the Zeya Basin, is a relatively recent feature, and that the river formerly flowed across this, or somewhere across this range, joined with the Songliao or the Sungari River, the Songhua River, and then flowed southwards into the Gulf of Bohai. And therefore, the pre-capture drainage basin of the Amur would have been much smaller, so about a third of its current size. And of course, draining only the basement terrains in the eastern part of the catchment. So that clearly would have a major impact on both the flux of sediment and the composition of sediment going to the delta through time. So that's really what we want to test in this during this talk. The model below is a kind of alternative model that I proposed. Has been largely untested. We'll come back to that at the end, where there is some kind of compelling evidence that the tributaries of the Sungari River, the drainage patterns look like they're mostly converging to the west. So there is a reasonable case to be made that this river system formerly did flow down to the Gulf of Bohai. And this is the elevation, the drainage divide here, the elevation is very low, a couple of 100 meters only. And it's a relatively recent feature. So we'll come back to that at the end as well. Okay, so one other thing I just want to mention, I'm not going to deal with this so comprehensively, but it is possible that the river system also flowed or had a different exit point in the past. So rather than the flowing all the way north here to its current location, that it may have cut across the Sakhalin mountain range, which is a dissected volcanic arc, and into the Tatar Strait further south, maybe 150 kilometers further south. We will touch on this in the presentation and kind of test this to a degree, this hypothesis. Again, there's some good reason to think that the valley here, where the river was proposed to have gone in the past, has very low elevation. This is only 1 or 2 meters above sea level here, most of these lakes, and the drainage divide here is only about 100 meters or less above sea level. In fact, the drainage divide here is only 2 kilometers from the shore. So this is a tributary of the Amur flowing to the west. So that's been used to explain the more southerly distribution of some of the older deltaic deposits on Sakhalin, which we will come to later. So this is really going to be a source to sink discussion, as I say. So we're going to look at the source. I'll talk a little bit about the geology of the catchment shortly in order to kind of frame the first discussion. We're going to look at the sediment routing system itself, how much sediment has been transported, and we're going to look at both the composition and the quantity of sediment in the sink in the North Sakhalin Basin. Okay, so a little bit more before we really get into it on the source, because we need to have a grasp of the geology of the source area before we go into it in detail. But you can see here that the way I've divided the drainage basin of the Amur into kind of three physiographic regions. The first one here, number one, which is consistent with what would have been, according to that drainage capture model, the extent of the Amur pre-capture. So this first area here is an area of very low elevation. The mid-Amur basin is actively subsiding or has been recently subsiding. Very low elevations, about 50 meters on average across this green area here above sea level. And it's bounded by these mountain ranges. So the Sakhalin to the east, which is a former volcanic arc, Cretaceous volcanic arc, and the Buryansky range or mountains to the north and west. A series of narrow ridges separate this region from the second area here. The central part of the catchment consists of a number of Cretaceous to recent sedimentary basins, mainly. So these are the yellow areas on this geological map here that are now being incised by the Songliao River and by the Zea River and the Berea River, which feed into the Amur. That itself is then separated from the upper catchment by the Khingan mountain range here, which consists mainly of Mesozoic andesites and basalts. And that separates the rest of the catchment from the upper area here, the Mongolian Plateau and the Yablonovoy Mountains, which consist mainly of Paleozoic granites and granodiorites, Paleozoic to early Mesozoic granites and granodiorites, and some very large batholiths here associated with a large igneous province, kind of late Paleozoic, early Mesozoic, large igneous province. Okay, so quite some good contrast in the geology, which means that this is promising for a source to sink study, because we should, in principle, be able to distinguish some of these source areas mineralogically and petrographically, and also in terms of sediment flux. Let's think about the sink for a second to try so that you have a good idea of what the basin looks like, into which the Amur is depositing its delta. So the North Sakhalin Basin, the line here is a cross-section across the plate boundary from the Sakhalin mountain range to the Daryugan Basin and the Sea of Okhotsk. So that's this cross-section here. So we can see here that we cross the Sakhalin mountain range, which is a Cretaceous to Paleocene volcanic arc. The contemporaneous subduction zone is recorded in an accretionary prism that's now crops out in the island of Sakhalin. So it's not entirely shown here, but it crops out in the southern part of the island of Sakhalin and the East Sakhalin Mountains. And the Cretaceous to Paleogene basin here within a four-arc basin that sat between those two areas. So that was the situation until the Eocene. And in the Eocene, the Okhotsk microplate, which is a distinct plate, microplate around with an extent around here, collided with the margin of Eurasia. So this went from being an active subduction zone and volcanic arc to being a strike slip plate boundary between a continental plate and a very attenuated continental plate to the east. And along this plate boundary was deposited a thick Eocene to recent depositional sequence, including the Amur from likely the Miocene onwards, the Paleo-Amur. Just to give you a little bit more detail about what's happened since then at that plate boundary, this is from the 2016 paper, which I'll talk about a reasonable amount through this talk. The plate boundary itself has then evolved from being a largely transtensional plate boundary in the early Miocene to middle Miocene, as shown here, when there was a very active subsidence in the North Sakhalin Basin. We have a phase of translation in the middle Miocene to latest Miocene, or the Miocene-Pliocene boundary, and then we have a phase of uplift starting at the start of the Pliocene, but really very significant uplift from the kind of mid-Pliocene onwards in the North Sakhalin Basin, both because of the propagation of far-field stresses from the plate boundary here, and also or because of rotation of the Okhotsk microplate. Okay, just to introduce you then to the geology of the island. So there's the topography on the left. There is a couple of strands of the main plate boundary here, the strike slip plate boundary. So you can see that you've got this stepped strike slip set of strike slip faults, another one in the offshore that's quite poorly defined. And then we have this very low relief northern part of Sakhalin. So very high relief, high mountain belts in the southern part of Sakhalin, very low relief northern area. And that low relief area corresponds to the North Sakhalin Basin. And all of the sediments here, so this is the North Sakhalin Basin again here, all of the sediments are Eocene, so early Eocene to Pliocene in age, with a little bit of quaternary, some quaternary sediments around the edge of the onshore part of the basin. So in terms of the stratigraphy, just to get your eye in again, the oldest rocks here are in the center of the Dagi anticline here, after which the formation, or the suite, takes its name. So that's the kind of early Eocene, very kind of sandy progradational part of the delta. The Okabekai is a much muddier unit that's mainly middle Miocene in age, so kind of outer shelf deposits that extend across the central part of northern Sakhalin. And the Nutov is late Miocene to Pliocene progradational unit again, or regressive unit, where the delta, where we have very sand-rich deltaic deposits across all of the island. So it's worth pointing this out, because I will refer to these. I'll try to make sure to refer to the ages as well, but I will refer to these three units in particular, the Dagi, the Okabekai, and the Nutov, later in the talk. The inferred drainage capture event is shown here. So there are two possible ages for this. One is late Miocene in age, and the other is Pliocene in age. So if this event took place at these times, then we should see that from the composition and the flux, or the sediment accumulation rates in the basin. Okay, now for the second part of this, so I'm going to talk on two sections here. The first part is going to be on the composition of the sediment, the provenance of the sediment. The second on the quantity of the sediment. So just to introduce you a little bit to the main kind of data set we're going to be using, the main data set that we use both for the Amur and for Sakhalin is heavy mineral analysis. So we looked at the heavy mineral composition of, the 1 to 2% of the sand that's made up of these heavy minerals, and these are much more source specific than the kind of framework grains, the quartz and feldspar and so on. But there are a few caveats to using this kind of data for provenance studies, as shown from this image from Eduardo Gazzanti. One is that not all grains are equal. So different processes, particularly weathering on the floodplains, weathering in the source area, abrasion during transport, hydrodynamics, and especially diagenesis, dissolution during burial, can have a strong overprint on the provenance of these kinds of these grains, or of what's preserved of these heavy minerals. And there's a fairly well understood sequence, and increasingly well understood sequence of dissolution that takes place. So pyroxene is particularly unstable, Amphibole is fairly unstable, as are staurolite, epidote, and titanite. Then we get into the kind of relatively stable minerals here, the garnets and apatites. These are somewhat susceptible to dissolution, particularly in the case of apatite, particularly surface weathering, so acid leaching in the kind of shallow soil profile. And then at the very far right of this table, we have the ultra-stable minerals, the zircons and tourmalines and rutiles. So these are very good for if you've got very mature sediment in your sandstone or in your sand. You're likely to be left mainly with these minerals here. So you can use stable minerals, i.e. ratios of some of these more stable minerals like garnet and zircon, or apatite and tourmaline are two classically used ones, to evaluate this. If you have very compositionally mature sediment, if you've got a lot of alteration occurring in some of these more unstable minerals, then you can use these more stable minerals, the ratios of them, to tell you something about sediment provenance in principle. We can also use single grain geochemistry, so look at the populations or different types of different species of garnet grains, for example, almandine and spessartine, and so on. I'm not going to talk about that very much today. We did quite a lot of that, but it's a little bit ambiguous in terms of the results. So I'm going to introduce you to some preliminary uranium lead age spectra of detrital samples, zircons from detrital samples from the Amur and from the older basin. And that really gives us a much better fingerprint of the source areas as compared to the more general heavy minerals, which could come from multiple areas. Okay, so in terms of sampling here and sample collection, I'm going to talk a little bit first about the Amur itself, and then I'll switch to Sakhalin for the Paleo Amur samples. So the Amur sampling was done by Sarah Pointer, one of my co-authors, and David McDonald during, I think it was around 2000. They did a cruise along about 1,500 kilometers of the river between Vlagoveshensk and Komsomolsk na Amur. So a reasonable section of the river and its major tributaries. So particularly on the northern side and the Russian side, not so much on the Chinese side, the Sungari, for example, or the Songhua. This is something slightly missing here. There was a section of the river that they couldn't sample because of a security zone. So there's a big missing data or a big data gap in here between the Khingan Gorge and Vlagoveshensk. But you can see what this kind of cruise looks like. This is the boat they used. So they just sailed along the river, stopped now and then along the sandbanks, collected a bag of sand, focused on a kind of fine to medium sand for petrography and heavy mineral analysis. Some of these are just photographs taken from that cruise, extending from the Zaya River and the Amur River before its confluence with the Zaya. You can see here that the Zaya is actively incising older Neogene sands here, so it's cannibalizing its own, the deposits of the form of the older, coming from the same river system. This image here is at the Amur as it passes through the Khingan Gorge, or the Lesser Khingan Ridge, as it's also known. And this image here is from Komsomolsk na Amur, where you get a very broad, wide river, again incising some of these basalts and debris flows in the bank of the river. Okay, now to show you some of the results of that cruise. So first of all, the petrography. These are just a series of classic QFL plots, quartz, feldspar, and lithic plots for sandstone petrography. For the river itself, on the main bar here, and some of the pie charts above that are for the individual tributaries that feed into it. And then the image below shows in a little bit more detail what the composition of the sand is in terms of individual components of the QFL plot. So monocrystalline quartz, polycrystalline quartz, chert, feldspars, plagioclase, and K feldspar, and so on. Only really one thing I want to point out from this is that there isn't very much change in the composition of the river in the upper portion. We really don't see very much difference between, albeit not very many samples, but between Blagoveshensk and the Sinden River, or just upstream of the Sinden River. We do start to see some subtle changes in petrography. So we see a flux of quartz coming in from the Sakhalin and some more lithic fragments, sedimentary lithic fragments, but that's fairly quickly drowned out again by the bedload of the river itself. So as we go further downstream again, we kind of revert to something that's pretty similar to what we saw more than 1,000 kilometers upstream. So not very much changing, at least from start to finish in the river. We do see some local, within the individual samples, we see some subtle variations within that, but nothing very, very drastic. If we then look at the heavy minerals, and just to get your eye into this one, I better explain what the colors are here. The pinks here are garnet, the blues are zircon, the yellow is sphene or titanite, dark green is calcic amphibole, light green is epidote, and then we have apatite in white, pyroxene in black, and then some other minerals above that. But again, we see quite a similar pattern here. We have you can see that the composition of the river from its upper reaches north of Blagoveshensk, or northwest of Blagoveshensk, and its lower reaches down near the river mouth. And in this case, actually, I've got some additional samples that I analysed after this work was done by, most of this work was done by Sarah Pointer, but I got hold of another group of samples from further down the river and filled that data gap. And again, we don't see a huge difference in composition. We see a slight increase in calcic amphibole as we get further down the system. The apatite, the stable mineral indices are fairly stable, stable in terms of their ratios from the upper Amur down to the river mouth. So again, the take-home message here is that we don't see a very significant difference coming from the tributaries. And what would we expect to see? Well, maybe a significant increase in pyroxene in particular, as we get a lot of sediment coming in from the volcanic arc. We do see an increase in calcic amphibole. We do see some fluctuation in the pyroxene in the trunk stream. We see quite a lot of pyroxene in the tributaries, but again, quickly, a little bit further down the river system, that signal is kind of lost. So again, the take-home message here is that the composition of the river doesn't seem to be very different at the river mouth than it is 1,500 kilometers upstream at Blagoveshensk. So it looks like the bedload of the river is dominated by sediment coming from upstream of Blagoveshensk. That's quite important for when we're considering drainage models of drainage capture, because then we would expect again to see a big change in the composition of sediment in the Paleo Amur to be much more like that of the tributaries down here, if that were the case. I'm just going to look at a couple of zircons just so you can see what the age spectra look like. So we don't have very much zircon data, but I have a little bit of data to share. And again, this just gives us a bit of a more specific fingerprint for the potential source areas. So on the bottom right here is a probability density plot so age spectra from zircon grains. In this case, it's really only the top one that I want to look at in detail. That's good. And even there, the sample number is quite low. We don't have enough zircons in this to get a really good data set here. So we only have 64 grains analyzed. But we can see some peaks that are fairly well developed. We have peaks that are around 100 million years, about 200 to 220 million years, 260 to 250, 260 to 70 million years. And then we have a kind of broad range of older Paleozoic and Proterozoic peaks. Some of these are looking at the catchment here, and I've got some crystallization ages of granites in particular on here. This is far from comprehensive. There just isn't a huge, or at least wasn't when this was done, a huge amount of published literature on crystallization ages from this catchment area. So some of these are distinct and some are less distinct. For example, this 100 million year peak could be from the Sakhalin range. We don't have any crystallization ages from there, but we know it's a Cretaceous arc, or it could be from the Khingan Mountains in here, which has a broad range of ages of 100 to 150 million years. The 200 million year peak could be from the Bereyinsky Mountains, with a published peak of about 220 million years for these granites, or it could be from some of the batholiths further up in the Yablonovy Mountains at 200 to 225 million years as well. Some of the others are a little bit more distinct. We have this 260 million year age peak, which doesn't, at least from what's been published and what's been compiled, there really is only one large set of batholiths that are now exposed and being eroded that correspond to that, the Khangai batholith, and I think some of those that extend beyond what's shown in this map here. And then the other thing to look out for, although it's not very compelling in this, we only have a couple of grains in each sample really, because of the small sample size. But we do see a couple of other peaks, well, not really peaks, but a couple of other grains of older ages that have crystallization ages of 2,000 and 2,500 million years, or 2 to 2.5 billion years. Now the really old Proterozoic rocks in this area are coming from the Stanovoy Mountains in the north here. And again, we have crystallization ages there of 1850 to 2100 and 2400 to 2600 million years. So that's something to look at for in other samples. This is not very compelling, but we'll see it again in later samples. So that's what we're looking out for. We've got a defined signature for the Amur. We've got in terms of heavy minerals, in terms of petrography, and we have uranium-lead age spectra from near the modern river mouth, but to which we can compare any paleo-Amur samples. So again, here in terms of sampling on Sakhalin, this is just some images from the fieldwork. This is my favorite mode of transport in Sakhalin to access some of the remote Schmidt Peninsula sections up here. But we did a lot of fieldwork all over Sakhalin, and we collected a lot of samples from all over Sakhalin. And the plot here just shows some of that data, but you can see some changes in the stratigraphy. You can see that the Pliocene samples look very similar compositionally to the modern Amur, as to some of the Pliocene samples in Schmidt and in northeast Sakhalin. We can see that changes as we get deeper in the stratigraphy, and it's very different down here. But if we plot the zircon tourmaline rutile index, which is a compositional maturity index, then we can see that the main issue here is not necessarily a change in provenance, or it's very difficult to extract a provenance signal from this because there's so much dissolution going on because of burial and because of surface weathering. Surface weathering is a big issue. If you remember earlier, I mentioned that apatite's particularly susceptible to weathering during erosion, and it's quite a good way to identify recycled sedimentary rocks, looking for a decrease in apatite tourmaline index. You can see that all the paleo-Amur samples have a significantly lower apatite tourmaline index than the modern Amur River. So what to do about this? Well, ideally, we would find somewhere where we can have a complete stratigraphic section. And to do that, I accessed a number of wells from a couple of offshore oil and gas fields, labeled here as Field A and Field B. So we've got core data, and we've also got cuttings data from the Oligocene up to the recent, or at least up to the Pliocene in this case. So these of course have no recent surface weathering. At least there may be surface weathering, but not recent surface weathering, not because of weathering in the present. So again, extracted heavy minerals from a number of these wells, and I'm just going to show you one plot, one well from field A to kind of summarize this. So again, here on the left, if you look at this bar, this vertical chart here, this just shows you the relative abundance of different mineral species as we go from the surface of the well at 0 kilometers here, 0 kilometers below the mud line, below the seabed, down to 3.2 kilometers or so in the Oligocene. And what we can see is a very strong and very clear change in composition of the heavy minerals with burial and with stratigraphy, perhaps. But again, we can see if we look at where these transitions are taking place. So we see calcic amphibole disappearing at about 1 kilometer. If we look at those amphiboles with an SEM, we see that they're covered at this depth. They're covered in edge pits and fat and other evidence of dissolution. Again, if we look at epidote down to about 2 kilometers, you can see again lots of evidence of dissolution because of burial in this case. So clearly in this case, because of, for these grains, because of burial. So we need to look at the stable minerals to see if there's any hint of provenance change. And what we see when we look at these different stable minerals, mineral indices, so garnet zircon index, rutile zircon index, apatite tourmaline index, and the yellow bars in the background here show the composition of the modern Amur system. So they are a reasonable range of composition. But most of these sit within that range, except for the apatite tourmaline index and perhaps rutile zircon index here, which I'm not quite sure what to do with. But we don't see a systematic step change at a particular depth, except here at about 2.5 kilometers. So at this point here, we see a significant decrease in the amount of garnet and apatite, and relative increase in the other grains. And then at above 400 meters burial, we see a significant decrease in the amount of apatite again. And we spent quite a lot of time interpreting this, but and I can't really go into the details of why that's the case here. But what we see in this area here, in the deeper part of the well, is a result of intrastratal dissolution, and possibly also dissolution on the floodplain during burial. We've done quite a lot of work in terms of breaking out the sequence stratigraphy of this section with a much more detailed set of samples, and seems that there's a lot of dissolution on floodplains going on. But the upper part here is in the Pamir, which is the kind of late Pliocene to recent, is a result of recycling of sediment from the onshore island of Sakhalin. So this is one way by which we can date the timing of uplift and recycling of sediment from the onshore, is from this sudden kick in the apatite tourmaline index in particular, also to a lesser degree in the garnets. So that's the stable mineral. So we don't see any clear. We see some fluctuations. We also see some fluctuations in the metamorphic minerals, for example, staurolite and a few other minerals, but nothing really compelling in terms of provenance change. And if we look at the zircons again, so in this case, I've got zircons dated from a couple of samples from the lower Miocene in the Dagi suite, a couple of samples from the upper Miocene in the Nutov. So this would be approximately the time of inferred drainage capture, and the recent ones that we showed already on top. You can see that we have the same, broadly speaking, we have the same clusters of grains or peaks of grains that we have in the modern system throughout all these samples. We have a few, maybe a little bit less of the kind of late Proterozoic grains in the Paleo-Amur samples. We have a lot more grains from the Stanovoy Mountains from up here in the Dagi, so in the lower Miocene and the upper Miocene. We have perhaps a little bit more input from the kind of from 100 million year old sources in the modern river system. So there are some subtle changes, but we see the same peaks and we see the same clusters that we saw before. So again, this suggests that we're likely to have had the same source area since 21 million years, though the absolute contribution of different source areas may have varied, and that makes drainage capture unlikely. I say unlikely because there are some caveats, of course, to this. We don't have all the crystallization ages from the basement. We don't have a lot of zircon data, and the heavy mineral data is somewhat ambiguous. Okay, so a couple of take-home points. The majority of the sediment in the modern river is coming from upstream of the King Anne Ridge. We have a minor change in sediment composition from the early Miocene to the present, and the provenance is relatively similar from the late Miocene to the recent. And I'm going to have to speed up here because I am short on time, but I'm going to talk quickly through the sediment budgets now in part 3. So this is just now, we're now looking at seismic derived sediment budgets calibrated by a couple of wells here. And we've got a very extensive seismic data set, all 2D data of different densities covering the Tatar Strait, the Uisdean Basin, and the northwest of Sakhalin, and the immediate offshore area. This is the assumed limit of deltaic deposition. And so using this data, we calculated a sediment budget by mapping the key horizons, depth converting, correcting for porosity, correcting for erosion from onshore Sakhalin. That's an important contribution. And then coming up with time average sediment accumulation rates. Now, I'm going to talk through this very quickly in the interest of time. So these are just a couple of seismic lines in the Tatar Strait showing the distribution of sediment. In particular, I just want to bring to your attention something that I'm going to use later, which is the geometry of clinoforms. So very well developed clinoforms in the south-flowing clinoforms that appear suddenly in the latest in the early Pliocene, in the uppermost part of the Neutov. And the rest of that I will pass over fairly quickly. In terms of the seismic stratigraphy, we've got I've shown 2 lines here, obviously a lot more data than this. You can see that the Amur here, which is the late Pliocene to recent, is very thick. There's a very thick wedge, 3 kilometers of late Pliocene to recent sediment in the northeast of Sakhalin. And the Neutov, which is the shown in the beige kind of color here, is very thick in the north, and then the orange and brown, which is pre-Amur, but the orange is much thicker in the south of the basin. So if we look at now a line from north to south, we can see that we have a change in the location of the depocentra through time. So we have about 200 kilometer shift in the position of the depocentra of the basin between the Dagi and the Neutov. So what causes that? Is it caused by deflection of the river mouth or by strike slip displacement along the Sakhalin Hokkaido shear zone? We can look at a number of other ways to try to understand the amount of offset along the main faults. So we see using reconstruction of lithofacies about 100 kilometers of offset along this main fault here. We can see from reconstructing piercing points, particularly normal faults, that we have about 60 kilometers of faults along this particular 60 kilometers of offset along this particular fault. So we have quite a lot of offset here. It's a little bit higher than what we would expect from the present day deformation rate or translation rate, but so there is some evidence that was higher in the past, but that's not too important for this story today. What we do see, though, is a significant change in clinoform orientations as well, from the early Miocene through to the lower Miocene, the early Miocene, the late Miocene, into the Pliocene and Pliopleistocene. And Paul, you asked about this earlier, but this is where the orientation of the clinoforms in the present day or in the recent sediments, very much confined by the uplifted island of Sakhalin. So that uplift again, and for reasons that I'm not going to go into here, is pretty well constrained, is occurring from probably the early part of the Pliocene and really kicking off in the middle of the Pliocene onwards. And that needs to be captured in sediment budgets. This figure here just shows how those sediment budgets are calculated. So these are just isopack maps from some of the subbasins on either side of Sakhalin. And of course, I mentioned that we had to correct for eroded volumes. So a little bit of trigonometry and surface mapping gave me a kind of a reasonable grasp of what the eroded volume was from the offshore basin. So that's all of that data was depth converted, corrected for porosity to give solid rock volumes. And here are the solid rock volume for the sediment budget for the Amur in since the early Miocene, essentially 21 million years. If we add all these sub-basins together and note that the most recent sediments here on the onshore part of the basin are negative values, that's what this gray stands for here. So the equivalent of 40 million tons per year of sediment being recycled from Sakhalin. Then we can come up with a sediment budget for the Amur River system. So the recent, as in the last 3.5 million years or so, we've had about 120 million tons of sediment per year being deposited, and much lower sedimentation rates, although comparable with the present day, going back into the earlier in the Pliocene and the Miocene. So the two exceptions. One is that we've got a much higher recent sediment flux and a much lower sediment flux in the middle Miocene. So what causes that variation? We will come back to that shortly. This diagram just gives you an overview of what's going on in the basin in terms of uplift, just to give you a grasp of what's affecting the delta. So this is the delta. I'm just focused in here on this one. From the lower Miocene to the Pliocene, we start to see significant uplift and erosion of the delta, the former delta plane, as we have transpression along that plate boundary. Okay, so this summary of this little section was that we see significant tectonic deformation, which modifies the Amur Delta and the location of the depot centers. We can constrain the uplift, the timing of uplift of Sakhalin. We can also constrain the amount of sediment flux coming from that uplifted part of the basin, since the Pliocene in particular. And when we look at the budgets, then the sum of the budgets for all the different basins, we can see a significant decrease in sediment accumulation rates in the middle to late Miocene, and a significant increase since the Pliocene after correcting for various factors. So what is going on here? Is this a function of drainage capture, or is something else going on here? Well, we'll address this in more detail shortly, but we do see from both the combination of data from the zircon uranium lead age spectra and from the total flux of sediment, and particularly from the zircons and the composition of the sediment, that it's pretty unlikely that the drainage system back in the early part of the Miocene, the middle part of the Miocene, was this small and draining these lithologies. There's no compelling change in sediment provenance through that time. There is increase in sediment flux sometime in the Pliocene, but we'll address that shortly. The alternative drainage model is still plausible. It essentially has not been tested. We have no samples from the Sungari River, the Tsinghua River, so we don't really know whether this is likely or not. It's a much smaller drainage basin, so that drainage basin alone would cut the total size of the drainage basin by about a third, a little under a third. So that's still possible. But if there's no major change in provenance, what controls the changes in sediment flux? Well, let's deal with the middle Miocene first briefly. Well, one possibility during the middle Miocene is that we had significantly higher sea levels. So the mid-Miocene climatic optimum was about 15 million years. And if I raise sea level by 100 meters, and actually the sea level is probably a little bit higher than that back in the middle Miocene, we actually inundate the entire mid-Amur basin with water. So one possibility is that the Amur system had its delta way back up in what is now one of the interior basins back in the middle Miocene. And that may account for why we have significantly reduced sediment flux and particularly very little sand deposited in the North Sakhalin Basin at this time. So that's one possibility. There are others, but we can maybe deal with them in questions. To account for the significant increase in the Pliocene to Recent, what accounts for that? Well, we've already accounted for the uplift of the North Sakhalin Basin, so we don't have to worry about that. There is inversion that occurs since about 2.5 million years in the Zea Basin, so in these internal drainage basins. That might account for about 10 million tons of sediment per year since that time, or averaged over that whole time interval. If this Sungari drainage capture event is possible, then that would contribute something like 6 million tons of suspended sediment load, so maybe 10 million tons, just using a ballpark number, somewhere between 6 and 10 million tons of total sediment load to the North Sakhalin Basin. But there's more than that going on, obviously, and it may just be that we see significant fluctuations in temperature, so increased erosion rates in some of the mountainous areas. We have no major glaciation here in the Pliocene to Recent, but there may be other things going on regarding just fluctuating temperatures, glacial interglacial changes in climate, and increased sediment flux. So to conclude, and I'm sorry I've run slightly over, but to conclude, we don't see any major change in sediment provenance since the early Miocene. Clearly, tectonic processes, particularly transpressional uplift in the delta, have an important impact on sediment routing and sediment budgets. There is a significant variation in the sediment flux from the Amur, but those are probably linked to climate, to sea level state, and to the inversion of internal basins, rather than to any major drainage capture event. And so therefore, large-scale drainage capture events are unlikely, and with the exception potentially of the capture of the Sungari and Songhua River, which is untested. Lots of questions remaining. Really, this is just the kind of first step to understanding the kind of long-term evolution of this river system. So we haven't got a very good handle on the contribution of individual tributaries. Really, they're too similar in terms of bulk petrography or heavy minerals to use those approaches usefully. So I think you'd really have to have a very well-constrained uranium-lead data set with large sample sizes from each river catchment and well-constrained crystallization ages in the basements to really nail this down, as well as samples and gauge station measurements from all these tributaries, and they're just not that easily available. We haven't looked at the mud size sediment fraction, so that's something that still needs to be done. We haven't really looked for evidence of marine transgression in the Mid-Amur Basin, so it's just a hypothesis, untested at this stage. And we have few samples of pre-Amur stratigraphy, and we haven't looked, for example, at the zircons in those data sets. And we really don't know what the major drainage basin, or what the drainage network was like in the earliest part of the Miocene and earlier. So those are my outstanding questions, but I will hand over to Paul to see if anybody else has any questions.
Thank you so much, Uisdean. And can you end the presentation mode? Are you able to check the chat?
Yes, so let me just see if I can
show. Just escape the, okay, now you can now. Okay, so as you can see, that Bob Allen mentioned, this system, thank you so much for this great talk, because the Amur River is we just know very, very little compare other major world river systems. This is a relatively unstudied river. So you provide such a great information, particularly from zircon, mineral point of view and tectonic history. I think we are learning a lot. So here Peter had also left. He asked a question, Peter Clift. He said he's wondering about the sediment capture in basins on shore.
Yeah, so the basins, the internal basins that I mentioned earlier, the Zea Basin and the Songliao Basin in China. The Songliao, I don't have very much data on, and we didn't have any samples from that area. But there is the it was an actively subsiding basin in the Neogene. The Zea Basin was subsiding in the early part of the Neogene and would have captured a fairly significant amount of sediment from the upper reaches of the Amur and from the Zea River itself and so on. So there is certainly a lot of sediment being stored or being deposited and stored for fairly long time periods in those basins. Of course, so that's one aspect of the kind of multi-million year timescale. That's not that well constrained at the moment. I had a go at it in a couple of the papers that have been published in this, and I've got that ballpark number of 10 million tons per year coming from the Zea Basin in the relatively recent, in the kind of late Pliocene to recent. But obviously captured a lot of sediment before that. That's not really fully factored into these sediment budgets yet. Then there's sediment storage on shorter timescales as well, of tens of thousands of years. There are very extensive floodplains in the Zea well, less on the Zea Basin, but especially in the mid-Amur Basin and the lower reaches. There's active subsidence. So a lot of the tributaries flowing into the mid-Amur Basin actually their bed load is deposited in a series of lakes and actively subsiding, in part of an actively subsiding basin in that area. So, yeah, there's a lot going on. It's a very complex area geodynamically as well. And I haven't really factored in dynamic topography into the equation and subsidence related to that. So, yeah, there's a lot of questions to answer, I think, to address in terms of storage of sediment within the basins.
Okay, cool. So is any question from audience? Let me see. Okay, now the audience, you can unmute yourself if you have any question. Okay, so let's wait. So audience, if you have any question, you can unmute yourself and directly ask. So let me ask you this. You show eastern side offshore of the Sakhalin Peninsula, the island, so the sediment. And so is any of those sediment are they from the local, that island, or they are somehow from the Amur River? Or how much?
So very locally around so there are ophiolites in the Schmidt Peninsula, and ophiolites are great because they have very specific mineralogy. So you can see their signal very, very clearly. Very locally around the Schmidt Peninsula in the north of Sakhalin, you see locally derived sediment, but you don't have to go very far before it's completely overwhelmed by the Amur. And the same when you go down to these Sakhalin Mountains. I see you see some distinct, particularly like green schist facies minerals that come from the mountains very near the mountain belt. But again, as soon as you're more than 10 kilometers away, it's drowned by the Amur. So the Amur is just such it overwhelms everything in the Neogene.
Good. And the big question: how about the annual sediment load, the current, the modern Amur River? How much sediment discharge?
So the number I've got quoted is 52 megatons a year, which is not that big for a river of its size. 52.
Yeah, but it's good size.
It's a good size, but it's not, it's not comparable. I mean, I worked quite a lot in the Colorado and the Western US as well, and that's more than 4 times the sediment load. Although it's much smaller.
That's usually 200, but now it's 0.
Yeah, true. Whereas the Amur is still, 50 or thereabouts.
Okay.
So it's hard, of course, to compare. I was, a little bit circumspect in comparing the modern to these paleo sediment budgets because, for one thing, it's only suspended sediment load that we have a grasp of. We don't have a really good grasp of the bed load. It's just difficult to reconcile these timescales of decadal kind of
understand
processes. Yep.
So is any question from the audience? So how about during the sea level low stand? So where the river flow to is flow to north, go to the Caspian Sea, or go to the Tatar Strait?
It has to. It does, but it goes both. You see the clinoforms that flow. That show that they've got active progradation both to the north and to the south. Presumably, you've just got a avulsion of the river at different times, and so it's sometimes the main distributary is going to the north and sometimes to the south. But it goes both ways, yeah. And it's certainly by the time when you drop sea level 100 meters, there is no Sakhalin Island, right? There's land between that whole bay between the two. So the river system, the area, the subaerial, the subaerial part of the delta extends right up towards northwest Sakhalin and then south to the Tatar Strait.
I see. Okay. So Jianpeng, do you have any question? Anybody have a question? Jianpeng, you are mute. We cannot hear you.
Yeah. Hello, Professor. I don't have any more questions, but I am interested in this topic because 3 years ago I prepared a manuscript to talk about the diatoms impacted by the currents around the East Asia emerging seas from Oxford Sea to East China Sea. I select some course, public course data. That's a very wonderful area because Amur River, it is a high latitude river, quite different with low latitude areas. For example, Red River, Pearl River. For me, I'm still learning this information. Sorry, I don't have any more questions. Thank you very much.
Yeah, I mean, it'd be interesting to see what comes of that if you've got extra core data. I mean, again, just to reemphasize, this is just for the first step in understanding this system, and with more data, there's a lot of refinement that could be done to this. Never mind, like so many new things that you could do to understand what the dynamics of this river system.
Cool. Yeah, I think you provide a long history, tectonic and river basin change. I hope if possible we can start a new collaboration there, understand the modern dynamic, how the current, how the sediment working with wave, tide, and maybe we can have that kind of dialogue.
Yeah, it sounds interesting. Yeah, the recent going back to the last glacial maybe is really it's a very interesting topic here, and it's quite wide ranging. I mean, it's quite a polluted river. I didn't appreciate that until I spent a little bit of time brushing up on this a couple of days ago and looking at heavy metal concentrations in the river. I didn't appreciate quite how high they were. So there are a lot of pollutants.
Because China, the northeast area, the province, Heilongjiang, and also the whole area is the heavy industry dominated area. So that's interesting. And also this river is the rank of the one of the river, the top 10 river, heavy plastic polluted.
Oh, really? Yeah.
Discharge a lot of plastic.
Wow.
Trash to the
there you
sea.
Go.
So
that's definitely in vogue at the moment. So it's to understand microplastics, right? That would be an interesting thing to address.
That's very good. We need to pay a little bit attention on this river and the nearshore environment. Okay, hopefully we have more dialogue, more conversation about this. So if we do any other question from the audience, we can stop here. Once again, this talk is available online, and if you want to rewatch this, double check this, it's available on our YouTube channel. But once again, next week we have 2 more talk about given by John Schwartz, Dave Morin, and Christoph one talk about Rio Grande River system, other one talk about Congo River system. Okay, thank you very much. Uisdean, thank you so much for giving this talk. I know your research is very, very broad, spread all the world. So I think in the future, I will schedule you talk about other river system. So how about the Indonesia one, the delta you mentioned?
The Mahakam. That's
Mahakam,
that's an interesting one. I mean, we're mainly focusing on the deep water, the deep water part of the delta.
Okay.
But that's quite recently published, so I can
think about that. If you get ready, you can give a talk. I will schedule you, because we don't have really any talk over that region yet.
Okay, good. I'll give that some thought. Yeah.
Sure. Let's keep in